Alrighty folks, today we're looking at position versus time graphs. I want to see if we can describe the motion of this object by looking at its position versus time graph. So we have one here. It looks like it's a nice linear position versus time graph. It's something with a constant positive slope. So let's see if we can figure out what that means. If I look at equal time intervals on the x-axis and I go ahead and look at those points, if I look over at the y-axis, it looks like for this linear position versus time graph, it looks like for equal time intervals, this object has traveled the same distance. So I would describe this linear graph as traveling at a constant speed. And the other thing that I notice is that since we're going up on the position versus time graph, it's getting to greater and greater values of position. So I'm going to describe that as moving in the positive direction. So we're traveling at a constant speed in the positive direction. Okay? All right, let's look at some more examples. I've got a red car and a blue car here. I have their position versus time graphs next to each other, and I want to determine who's moving faster. So I think if I look all the way out at the end here, the blue car obviously has not traveled nearly as far as the red car has traveled. So I would say that the red car must be moving faster because it was able to travel a much greater distance in the same amount of time. But graphically, how would I describe that? What's different about the red line versus the blue line? Well, the red line has a much greater slope. So when I look at the slope of that line, a steeper slope represents a faster speed. So this blue line that's very shallow, we know this object hasn't gone very far in this amount of time. So we're going to look at that steepness of the slope to determine who's moving faster. And here's another example, the red car and the blue car again. And if we use the same strategy, they're definitely different graphs. Something's going on here at the beginning when we first started our timer. And if I look at the end, well, it seems like they've both gone the same distance from where they started. So if I'm looking at the y-axis, the position, and that makes sense because they seem to have the same slope. The steepness of their slope is the same. They seem to be parallel. So I would say these are both traveling at the same speed. What's different is just their starting position, right? It seems like the red car took a head start. Maybe the red car started at the 20-yard line on the football field while the blue one started at the goal line, right? So they're just starting in different positions, but they are traveling with the same speed. Would you say that the blue car is ever going to catch up to the red car? Right? If these lines are parallel, then obviously not. What would it mean on a position versus time graph for that blue car to catch up? Okay, in our next example here, we're seeing an intersection. And that means that for my blue object and my red object, at this time, they share the same position. So that's what it would have looked like if our blue car was able to catch up, right? Any intersection that we see on a position versus time graph just means that at that time, they share the same position, okay? Something different is going on in this one. The blue line is going down on a position versus time graph. It does seem to be steeper, so I would say the blue car is faster, but it's traveling to lesser and lesser positions or lower positions. So I would say that that's traveling in a negative direction. So our blue car is traveling at a larger constant speed in the negative direction. And our red car, again, a red object, is traveling in the positive direction with a lower speed than the blue car is. Okay? So we've mentioned that we can use the slope to help us with the speed. It's also going to help us with the direction, because the one thing you should notice about the red line is that, well, if I were to pick 2 points, and I like to segment these off, I just pick 2 points, draw a line through them, and imagine calculating the slope. Pick another 2 points, draw a line through them, and imagine calculating the slope. What I'm getting if I calculate any of those slopes is I get the exact same value every time. It's a constant slope. But the one thing I want you to notice is that every one of these slopes are positive. So these represent a positive constant velocity. So the red car is moving with a positive constant velocity. How do I know that? How do I know the slope is going to represent the velocity? Well, slope is rise over run. And on a position versus time graph, rise is change in vertical and run is change in horizontal. So that would be the change in position, my vertical, over the change in time, which is my horizontal axis. But what is change in position over time? That's just average velocity. So when we look at the slope of a position versus time graph, it's giving us a representation of the velocity. So how do we know the blue car is moving in the negative direction? Well, if I pick 2 points and draw a line through them and calculate the slope, pick 2 points later on, draw a line through them and calculate the slope, what I'm getting is a constant negative value. So the blue car is traveling in the negative direction with a constant velocity. Okay? So we can use the slope of the position versus time graph to figure out what's happening with our velocity. Well, we've only seen linear position versus time graphs. What's going to happen when our position versus time graph is curved? Something like that. So I'm going to use the same strategy. We know that the slope of the position versus time graph represents the average velocity. But I'm going to take it and I'm going to segment it. So I'll pick 2 points at the beginning and I'll draw a line through them. And I'll imagine calculating the slope of that line. And then I'll do the same thing later, pick 2 points, draw a line through them, and then even later, pick 2 points, draw a line through them. And what I'm noticing about these slopes is, number one, they're all positive. And number two, they're getting steeper and steeper and steeper. And steepness on a position versus time graph correlates with speed. The steeper this position versus time graph is, the faster I'm going. Think about it as covering a larger distance in a short amount of time. So this object that started out pretty shallow, almost flat, and it's getting steeper and steeper and steeper. So I would say that this object is traveling in a positive direction and it's speeding up. So all of those slopes are positive and they're getting greater in value. So we have something that's speeding up while traveling in a positive direction. So we can do this for all of our position versus time graphs. We can predict a velocity versus time graph. So I'll go through each of our examples here. We can start with something traveling at a constant speed in the positive direction. Well, constant speed in the positive direction means you have a constant positive velocity. So on my velocity versus time graph, I'm going to want to fill in values that are up here in the positive world, and they're going to pick one value and they're going to stick with it. So we have a constant positive value. Very similar when we are traveling with a constant speed in the negative direction. I'm going to have on my velocity versus time graph, I'm going to pick a negative value, so down here below the time axis, and I'm going to keep that value constant. So we're traveling at the same speed, but in the negative direction. Okay? All right, how about those curved position versus time graphs? We've already done this one where it's speeding up in a positive direction. I want to use that strategy of segmenting. So it seems like the slope at the beginning is roughly 0 or very, very low. So I'm going to go to my velocity versus time graph and I'm going to put a point. I'm going to say, okay, at the beginning, the velocity was very low. It was roughly 0. You can't get any slower than that. So this object is obviously speeding up. And since all of our slopes, if we keep segmenting and looking at the slope, all of our slopes are positive, I'd say it's speeding up in the positive direction. So later on, the slope is a large positive value. So my velocity later on is a large positive value. In between, it was a middling positive value. So I'll put something like this, and then I'm going to draw a straight line through them. And I'll just make a note about that. A velocity versus time graph, we're not going to see in AP Physics 1, we're probably not going to see a lot of curved velocity versus time graphs. And the reason for that, when we developed the kinematic equations, we said they only work for constant acceleration. A curved velocity versus time graph means that the acceleration is changing, and you would need calculus to handle something like that. So that's where our kinematic equations would break down, and we'd have to do something a little bit more complex. So really dynamic motion, changing accelerations. They may ask you to talk about it qualitatively, but we wouldn't have to do anything mathematically for a changing acceleration. So that's why I drew this velocity versus time as a straight line. I have an object that's speeding up in the positive direction. The velocity started at 0, and then it headed towards larger and larger positive values. Okay? Let's try another one. What if we had something like this? So I'm going to continue with one moving in the positive direction, going up on a position versus time graph. So we're moving in the positive direction. But if I segment this and I draw my dots and I draw a line through, do one in the middle, and then do one at the end, I can see now that while all my slopes are positive values, they seem to be decreasing because the steepness is decreasing, or this particular position versus time graph is getting more shallow. So on my velocity versus time graph, I'm going to start with a large positive number. That's a large positive slope. And then at the end, I have a slope that's nearly flat, or maybe 0. So later on, I'm going to have a velocity of 0, and in the middle, it's a fairly small positive value. So I'll put one in the middle, and I'll draw a straight line. So what is our object doing? Well, if the slopes are decreasing, if the velocity is decreasing, we are slowing down, but traveling in a positive direction. Okay, I've got 2 more here to practice, and then we'll do a challenging one. Okay, so let's try something like this. Okay, so I'll segment it off. I'll draw 2 dots close together, draw a line through. 2 dots close together, draw a line through, and 2 dots close together, draw a line through them. And I'm imagining calculating the slopes of these lines. And if I were to calculate those slopes, I think hopefully you notice that they're all negative. So this is something that's traveling in the negative direction. Again, it's going down on a position versus time graph, so that makes sense. It's also very steep at the beginning, and it's heading to flatter and flatter slopes. So this is something that is slowing down in the negative direction. So I want to start my velocity versus time graph with a very large negative number. This is a very steep negative slope. And at the end, I have almost flat or 0 slope. So to show the object is slowing down, notice that my velocity versus time graph is heading towards 0. It's getting closer to 0. So velocities that are closer to 0 mean that it's not moving very fast. And velocities that are further away from 0 means that it's moving faster. Okay? And the last one here, just going to move this out of the way. Let's do something like this. So it's moving in the negative direction, right? Going down on a position versus time graph. But if I were to segment this off, draw a line through those 2 points, I'm starting out very, very shallow. And then as I go on, I am getting steeper and steeper. But each of those slopes are negative. So I'm speeding up while traveling in the negative direction. So I'll do the same thing here. The initial slope was roughly 0. So my initial velocity is very low, or 0. And then as time ticks forward, the slope gets steeper and steeper and steeper, but negative. So I'm going to pick a large negative value, and my velocity versus time graph is going to look like this. Okay? So we'll summarize these again at the end, but we can get our velocity versus time graph from a position versus time graph. All right, let's do a little bit more challenging one, maybe one where it changes direction. So I'll do something like this, where we see multiple stages of motion. Okay, so definitely a little bit more challenging. I have the first portion, the first half of the motion, where it's going up on a position versus time graph. So here I'm moving in the positive direction, and then the second half where it's going down on a position versus time graph, it's moving in the negative direction. So something happens right here that it changes direction and flips from going positive to negative. I'm going to segment off the first half and look at my slopes. Looks like a very large positive slope at the beginning, and then here towards the top of the path it seems to get very flat, still in the positive direction. So I'll start with a very large positive velocity, and then I'll head towards 0. Okay, and that would be the first half of that motion where I'm slowing down in the positive direction. But after that, if I were to again segment this off and look at the slopes, those slopes begin to go negative. And they're also getting steeper and steeper and steeper. So at the beginning of this first half, the slope was very shallow or close to zero, and then later on it's a very large negative number. So what we have now is speeding up in the negative direction. Okay, so we have slowing down in the positive direction and then speeding up in the negative direction. This would be like something that you threw up into the air, right? As it's traveling upward, it's slowing down. At the stop, very briefly, the velocity is zero, and then it switches direction and begins to come down. And on its way down, it's speeding up. Okay, so now that we've done that one together, would you like to try one like this on your own? So see if you can produce the velocity versus time graph for that. Okay, so let's see how you did. We have a very large negative slope at the beginning. We have a flat slope in the middle, and then a very large positive slope at the end. So I would say that this is something that was initially slowing down in the negative direction. So these large negative slopes were getting more and more shallow, and then in the positive direction we were speeding up as these slopes are getting steeper and steeper. So we have slowing down in the negative direction and then speeding up in a positive direction. Okay? Awesome. So let's just summarize everything we've done. So those position versus time graphs, we know if they're a straight line, and then we're traveling at a constant velocity. So we'll just pick the velocity value, and it'll be a flat line on a velocity versus time graph. But when a position versus time graph is curved, it means that the velocity is changing. So speeding up is going to be getting steeper and steeper. So these two right here, we see the graph of our position versus time getting steeper. So those both represent speeding up. And then if our slope is getting more shallow, our position versus time graph shows that it's slowing down. For velocity versus time graphs, we're just going to read the velocity value from the y-axis, right? A velocity that's close to zero means you're moving very slow. A velocity that's further from zero means you're moving really fast. But the note that we made was a curved velocity versus time graph is a very dynamic problem. It means that the acceleration is changing. We'll be able to discuss it. If you had a graph, you could make some qualitative claims about it, but you're not going to be asked to do anything mathematical with that because it would require calculus to do that. Okay? So that's it for our motion graphs. Thanks for watching.